Hi guys, this is our first Flip the Classroom lesson of Chapter 6. In this lesson, we are going to talk about dot products of vectors and some things we can determine using the dot product of vectors. Now, in general, we've talked about vectors being multiplied by scalars or constants, but we haven't really talked about how we can multiply vectors themselves. And there are two ways to do this. And the first way we're going to talk about multiplying vectors themselves is the dot product, or the interior product, right? So right here, if we have a vector u as ab and a vector v as cd in component forms, respectively, then we say the dot product of our vectors u and v is the product of the horizontal components of the two vectors plus the product of the vertical components of the two vectors. So right here we've got vectors u and v. So right here we could say u dot v is going to be basically, when we take the dot product of these two vectors, we are multiplying first the horizontal components, so it will be 2 times 8. And then adding that to the product of the vertical components, 7 times 3. And that gives us 16 plus 21, or 37. Now, right here, we're basically getting one number, so we're not getting another vector. And we're going to talk a little bit about what this number, the dot product, represents. But first, what we're going to do is just sort of look into some properties of the dot product. And go ahead and examine some of the ways that dot products interact. So right here, in general, we say that the dot product of u and v is equal to the dot product of v and u. And we call this property the commutative property. So we can say dot products are commutative. It doesn't matter what order we take the dot product in. We say that the dot product of a vector and itself is equal to the magnitude squared. We're going to look more at that in a second. The dot product of the 0 vector and u, or any other vector, is always going to be 0, right? We say that if we're taking the dot product of a vector u and the sum of two vectors, we can basically distribute the dot product through the addition, right? So we are really saying we can distribute dot products through addition or subtraction here. But so what we'd say is the dot product of u and v plus w is equal to the dot product of u and v plus the dot product of u and w. But we can't say the same thing for scalar multiplication. So right here, when we are multiplying a vector by a scalar and taking the dot product, we can basically say that the scalar will either multiply to one vector or the other, or we can take the dot product of the two vectors and multiply the scalar with that. So right here, some general properties of dot products, and we want to take a little bit of a deeper look at using the dot product to find the magnitude. So right here, with our second property of dot products, basically what we've said is that the dot product of a vector in itself is equal to the magnitude squared. So right here, if we take the dot product of u and we get the magnitude squared, then right here, if we take the square root of the dot product with the vector in itself, we are going to end up with just the magnitude. It's a little, it's a pretty intuitive way of finding the magnitude. It's not really a shortcut, but it's worth sort of taking a look at. So right here, if we take the dot product of u with itself, right, we will have 4 times 4 plus 3 times 3, right? Product of horizontal components plus the product of vertical components. And that is going to give us, right here, our 16 plus 9, which is 25. Now right here, taking the square root of the dot product of a vector in itself is going to give us the magnitude of u as 5. So right here, we can use the dot product to determine magnitude in that way, but it's, I mean, in some senses, if we have the horizontal and vertical components, then it's really the same thing as just finding the magnitude itself. All right, so we can use the dot product to determine what we call projections of vectors onto other vectors. So right here, the projection of the vector u onto the vector v. If u and v are non-zero vectors, the projection of u onto v is given to us with this notation right here, where we're saying the projection of u, let's see, projection of u onto v is right here, the dot product of u and v over the magnitude of v squared times the vector v. So really what we have here is a scalar, right, that we're getting from the dot product over the magnitude of v squared, right, times the vector v. So basically what we're going to be doing graphically is really altering the length of v. And what we can say is that the projection of the vector u onto the vector v is really the component of u that is going in the v direction. So basically right here what we're saying is we drop a perpendicular from u onto v, right? We can see that we've got this much of u going in the v direction. Now, if we are thinking about a vector with standard representation, right, so extending from the origin, right, we can see the horizontal component as the x value and the vertical component as the y value, right? So really what we're saying here is by dropping this perpendicular from u onto v, right, we're seeing how much of u is going in the v direction, just like we're seeing how much of this blue vector up here is going in the horizontal direction, right? We're just sort of tilting this process. So right here, what we're actually getting with the projection of u onto v is the component of u going in the v direction. Okay, so squeeze that in there. Let's see if we can move this over and maybe make it a little more legible. Direction. Okay, so at this point, what we're going to do is have you guys pause the video, right? We've got the vectors u and v given to us in component form right here. And what I want you guys to do right now is to just first set up the projection of u onto v with our formula right here. And then we're going to unpause the video and take a look at it. And then after that, we're going to actually evaluate the projection of u onto v, which is going to be, of course, this vector right here that we've outlined in black. So projection of u onto v, or how much of u, or the component of u that is going in the v direction. So right here, we'll pause the video and give this a shot, and then we'll come back and look at it together. Okay, so first just set it up, and then we'll unpause the video and take a look. So right here we've got it set up. We've got our two vectors, u and v, and we're going to take the dot product of those in a second, over the magnitude of v, and then I forgot the square. So the square needs to be right there. And right here, when we evaluate what's inside the parentheses here, we're going to get one number, which is going to be basically the scalar, right, k, that we're going to multiply our vector v by in order to get our projection of u onto v, which we're seeing right here. So when we pause the video, evaluate that scalar, and then distribute it into the horizontal and vertical components. Okay. All right, so right here, evaluating the dot product in the numerator, we get horizontal components, the product of horizontal components plus the product of vertical components gives us 34. And then right here, when we square the square root in the denominator, we're going to get 8 squared plus 2 squared gives us 68. We can simplify that scalar down to 1/2, and then we get the projection of u onto v as being the vector 4, 1. So right here, our vector 4, 1 is the projection of u onto v. And if we evaluate it from with standard representation right here, we would say our horizontal change is 4, which looks right, and our vertical change is 1, which also looks right, and that's the projection of u onto v. So now that we've defined the projection of u onto v, we can start answering this question of what is the dot product. Right here, we can go ahead and take the dot product of our u and v. So right here, the dot product of u with v would be right here our 3, 5 dot 8, 2. So that's going to be the product of horizontal components, which is 3 times 8, or 24, plus 5 times 2, or 10, which gives us right here 34, right? The dot product. What is this number? And what we're going to do is we are going to take the magnitude of v and the magnitude of the projection of u onto v. So right here, we know that v itself is our 8, 2. And when we take the magnitude of that, that gives us 8 squared plus 2 squared, or right here our 68, excuse me, square root of 68. And right here, if we take the magnitude of the projection of u onto v, that's the magnitude of the vector 4, 1, which is going to be the square root of 4 squared plus 1 squared, gives us the square root of 17. Now, what we're going to see is that when we multiply the constants of the magnitude of v times the magnitude of the projection of u onto v, we get the square root of 68 times the square root of 17. And if we type that into the calculator, that's going to be the square root of 1,156. And if we evaluate that in the calculator, that's going to be 34. So right here, what we're sort of seeing is that the dot product of u and v is the same of the product of the magnitude of v and the projection of the magnitude of u onto v, right? And that's really what we're seeing here when we take the dot product. It's going to be the projection, the magnitude of a vector, times the projection, the magnitude of the projection of the other vector onto that vector, right? So we're really multiplying the magnitude of v with the magnitude of the projection of u onto v. And since we know that the dot product of u and v is equal to the dot product of v and u, we can infer that right here the magnitude of v times the magnitude of the projection of u onto v is equal to the magnitude of u times the projection of v, the magnitude of v onto u. So right here, we haven't actually proved this, we've just sort of talked about this with numbers. What I'm going to do is make another video that's the proof of this. I'm going to set up the proof of this, and then I'm going to give you guys an opportunity to sort of walk through the proof on your own. I'll set that up as an optional video. But as we start to talk about the proofs of, trig functions and these formulas of vectors, I want you guys to feel like these are coming from somewhere. So I strongly encourage you to take a look at that proof and to give it a shot on your own. But that's the end of this first video, and we're going to come back to the second video, and we'll see you there. Okay.